Math313, number theory, lecture 31, take 3, action. All right, we're in the home stretch. What I want to do now is talk a little bit about elliptic curves and applications. So we talked about the congruent number problem. If you are a number theorist, this could interest you. You know, which integers can be written as the area of a right triangle with rational sides? If you talk to the everyday person on the street, they're going to say, and we've spent how much money on this? Your responses are then countered with, well, you know, if you look at like the superparticle accelerators, you look at how many billions and trillions they cost you, we're really cheap on a relative scale. But this is not going to win you that much support for number theory. You know, most people do not care about the congruent number problem. So the question is, why would we care about elliptic curves? So the great mathematician G.H. Hardy, and if you want to be a mathematician, I strongly urge you to read his apology, where he is basically talking on his deathbed about his life spent doing mathematics. And he says, well, you know, I console myself with at least nothing I did would make any difference in the world for good or for ill. I've at least been neutral. And it turns out a lot of the mathematics he does now has applications in number theory and cryptography. And not surprisingly, this is where elliptic curves are going to come into play. We're going to talk about elliptic curve cryptography. So in terms of applications, cryptography is one of the most important in 21st century society. We need to be able to send information securely and efficiently. And there's often a huge trade-off between the two. So sometimes you have very involved systems. Now the difficulty is, how do you prove that something can't be done? Right now, RSA is built on a premise. So we discussed RSA earlier this semester. What is the premise behind RSA? Very hard to factor. So factorization is hard. Division is easy. So if I give you two numbers, if I give you, here's the product of two primes, and here's a candidate, it's very easy to check and see, does that number divide? It's very hard to factor the number. And the reason we say it's very hard is a lot of smart people have tried this for centuries and no one has come up with an answer. Or maybe there is an answer. If somebody has a fast way to factor numbers, do you think that they would spread this to the world? No. You give this to certain organizations, and those organizations then can crack anything that uses RSA encryption, or encryption based on factorization. So I do a lot of work in Benford's law of digit bias. This is used by the IRS to detect tax fraud, among other things. Unfortunately, it's now been published that you can use Benford's law to detect tax fraud, or to at least indicate that it's likely. So now accountants know that when they're submitting things, they should do a Benford check. Or if you're making up numbers, you should make sure things pass a Benford check. You don't want people to know sometimes what you're able to do. A lot of times, even decades after the events happen, it's still classified how one knew things. You know, that certain codes were cracked. It was a long time before it came out that we cracked the German Enigma, or that certain methods are compromised. Because if you know that a certain method is compromised, you may know, oh, okay, they've been reading our messages for the past 10 years. They know that all these things were done. It can change greatly how you act. So the whole point is we want problems that seem hard. If you want a good movie on this, the movie Sneakers, anybody ever seen the movie Sneakers? It's one of the few movies that talks about mathematics which is plausible. There's a great scene by a mathematician talking about a way to possibly factor numbers quickly. And they use at least the correct buzzwords, and they have the correct math in the background. All-star cast. Wonderful, wonderful movie. So what I want to do today is I want to talk about the Diffie-Hellman key exchange for elliptic curves. So Diffie-Hellman key exchange on elliptic curves. So this is one of the biggest problems, is how do you communicate with somebody you have not met? If you have met somebody, you might be able to agree upon a secret. And you would hope that you could write down that secret in such a way that only the two of you know it and there's no danger of it being compromised. I've been reading some books that talk about how people can anonymously hack into your phones and turn it on, make it into a recording microphone, and listen into what's going on at your place of work. Or that if your phone is connected to the wireless, people can actually access information off your phone. You've got to be extremely careful what's out there. So if you can meet with somebody in secret, agree upon a secret, and then part, and each of you can keep that secret and keep it secure, that's the best way. Especially if you only use that method to communicate once, and then you destroy it, and then you use something new. Because the more times you use a system, the more vulnerable it is to analysis. One of the best is if you just do like a letter substitution. The longer the text, the more times you use it, the more likely you are to guess the frequencies. So the whole point when we did RSA was we had two people agree upon a secret. Anybody remember how we did this? This is the end of the semester. This is a great way to review what we did. So how do we agree upon a secret?
People came up with a secret power.
Yeah, so we knew that there was a generator G. And I think we looked at G was a generator of maybe Z mod PZ star. Is that we had a whole series of exercises that proved that this was a cyclic group. And then you have Alice, who chooses an A, Bob chooses a B, and Alice yells out G to the A, Bob yells out G to the B, and then they both can figure out G to the AB. And if you have an eavesdropper Eve, she knows G, G to the A, G to the B, and she knows the prime P. This is what's public. And there is no known good algorithm to figure out what A and B are. This is called the discrete log problem. If these were just regular numbers, well, look, take the log of G to the A, divide by the log of G, and that's A. It's the power law of logarithms. Why is it so much harder on Z mod PZ star? It's cyclic, so...
And so like G to a power can be lower than G?
Yeah, it's the modular arithmetic that makes this hard. So what's wonderful is it's very easy to calculate G to the A and G to the B using fast exponentiation. Even if A is a huge number, we can calculate this quickly. And the numbers stay small because of modular arithmetic. So RSA is a really good system. What is RSA built upon? Or what is the Diffie-Hellman key exchange in this situation built upon? It's built upon this discrete log problem being hard, and it's built upon the structure of this cyclic group Z mod PZ star. So one of the things we do in mathematics all the time is we generalize. We have a nice group structure here, and we're using this group to build a key exchange, a way for two people to yell in public. Maybe we could somehow do this with elliptic curves. And that's the whole idea. And what would you hope would be true about the group on elliptic curves relative to this cyclic group? So what would be the hope? So maybe there's some kind of generator. Do we want it to be isomorphic to Z mod PZ star? If it's isomorphic, is there really a gain? So maybe we want it to be a group that's harder to work with. And maybe if it's a group that's harder to work with, it will be more secure. So this is the whole point, is that by changing the group we look at, we have the possibility of doing similar things, but maybe they'll be harder to crack. And what this could mean is you could get the same level of security for smaller values of the parameters and smaller runtimes. Frequently, the way a lot of this stuff works is you use these very intense systems to exchange a secret. And then you might use that secret as the key phrase in a letter substitution or Vigneri cipher or something that's much faster to run. And you have one big calculation in the beginning and then boom, 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 boom. But it all comes down to, can you find a difficult, challenging group? And so this is exercise 9.33 from the book, the Diffie-Hellman on elliptic curves. So we've done a little bit of work right now with the group structure of elliptic curves. Enough to see that it exists, it's commutative. If you start off with rational stuff, you stay with rational stuff. But the formulas are much more involved. Right? And so the hope is that we can use this to somehow build a nice group. Now, we want something that's finite. It's possible that the elliptic curve groups could become infinite. So we're going to look at elliptic curves, but we're going to reduce everything modulo p. So instead of forcing x cubed plus ax plus b to by squared, we'll say, just by squared up to a multiple of p. So given an elliptic curve E, y squared equals x cubed plus ax plus b, study mod some prime p. And then we can form a group law here, and we can do all the calculations similarly. And now what we want to do is we want to generalize the Diffie-Hellman key exchange. So what's the first thing we should choose? So we need to choose an analog of G. So it turns out that this group is not going to be cyclic. So choose a point of prime order, and I hate the fact that they use n for prime order. I will talk to the author. Whenever I see n, I do not think of a prime. I will keep this so it's the same notation as in the book. I would much rather use q. So they want a point of prime order and say p. And this means np is the identity. It's our point at infinity. And n is the smallest that works. Okay? Does that seem similar to what we had over there? Yeah, this is giving us like a cyclic subgroup inside the group of rational solutions modulo p. Or inside of the group of solutions modulo p. What would you do next now? So np just means you add p to itself n times, and you get the point at infinity. We've got our essay over here. What should we do now? Yeah. So Alice chooses an A. Bob chooses a B. So what should Alice compute? So what would be the analog of G to the A? So over here, when we have G, G was the generator. So what does it mean for G to be the generator of Z mod PZ star? Every element is a power of G. And what's the highest power we could have? Right, and what's the order of Z mod PZ star? P minus 1. Right. How many numbers are relatively prime to P? It's P minus 1. So G to the P minus 1 is congruent to 1 mod P. And no smaller power would have this work. That's what and then every power now of G is going to be distinct. If two powers of G were the same, then with a little bit of algebra you could show you would have a smaller power of G that when you raise G by that, you would get 1 mod P. So this is what it means for G to be generated. We get everything. P minus 1 is the smallest. And now we're going to calculate G to the A, G to the B, G to the AB. So we have to figure out what would be the analog on an elliptic curve. I can't raise P to the 8th power. What would it mean to raise a point to a power? What could I do instead?
Multiply A and P.
I'm sorry?
Multiply A and P.
multiply A and
P.
P.
Big P.
Yes. So we could do A, P. This is going to be P, A copies of P. And that will be a new point. And what should Bob do? B times P. And then they can both calculate ABP. And the reason is Alice knows Bob is yelling out BP, so she just has to add this A times. Bob hears Alice yell out AP, and he just has to add that to itself B times. So they've both now been able to compute ABP. They now have a secret. What does Eve know? She knows the elliptic curve. She knows the prime. She knows the little point. She knows AP. She knows BP. Maybe she knows N. I mean, does Alice know N? Did they yell at N? So they're saying that you keep little n secret. So someone has to, I mean, either Alice or Bob can know what n is. The other one doesn't need to know. And so this is very similar to the RSA stuff. The difference now is we're doing things on an elliptic curve with a slightly more involved group law, with a slightly more involved group structure. And the hope is that this makes the discrete log problem harder. Is, knowing these points, can you recover A, can you recover B? And her goal is find A, B, or A times B. So, again, elliptic curve cryptography is an enormous subject. This is a, maybe 10, 15-minute introduction to it. The goal is to show you the stuff we're doing is already enough to have major implications in the world. This is not just theoretical stuff. Then the question becomes, what are the possible group structures of an elliptic curve? And I can look at group structures over both the integers. I can look at group structures over the rationals. I can look at group structures modulo p. And I can use these to build different groups. And I can try to do things with these different groups. And then we may have some time to talk about this. This is the last week trying to tie things together with the local global principles of trying to build a generalization of the Riemann zeta function, looking at the number of solutions mod p. This is related to one of the biggest problems in mathematics, the Birch-Swinnerton die conjecture. So this all leads to great stuff. I want you to have a sense of what's out there. So last week we were talking about algebraic geometry. This week we're now talking a little bit about elliptic curve cryptography, and maybe a little bit of how you figure out the structure of the group. And it turns out that the L function you build, this generalization of the Riemann zeta function, if you look at it at special values, it tells you an enormous amount about the structure of the group. This is very similar to when we looked at the Riemann zeta function at special values, we got information about the primes. So this whole idea of this local to global passing is one of the big themes of the course. Okay. All right, so this is just a really nice application of what we have been doing. So now we're going to just go back a little bit, and the question is how much detail to go through in analyzing the addition of points on elliptic curves. So you're all supposed to have read chapter 9 by now. There's a lot of pages of algebra. And this is where, if you've seen those shirts and you do the algebra, then the miracle path simplifies nicely. So at the end of the day, we get a lot of nice formulas. So what I want to do is I want to just assume those formulas and not go through the tedious algebra. It's straightforward. We have equations. We have a cubic equation. We have 2 roots. We can find the 3rd root. We can go through and do all this stuff. We have to be careful. What if the 2 points are right on top of each other, so they're additive inverses? Then we're going to add to the identity. You have to go through those cases. I want to do the big picture stuff and just give some of the formulas. So adding points. So we'll have y squared is x cubed plus, am I using capital A or lower a? Lower a. Ax plus b. And we'll assume P and Q are 2 points such that P plus Q does not equal the identity. Well, if P plus Q does equal the identity, then I know what's going on. So we'll assume we stay away from 2 points like that. And we want to figure out what's the x coordinate of P plus Q and what's the y coordinate of P plus Q. So if I have my elliptic curve here, so let's say here's my P, here's my Q, and here's P plus Q over here. I have a line, and I can write this line as y equals mx plus t. So I'm making sure I'm using the notation in the book. Yes. So why would I use t for the intercept? Right? This isn't how we normally write equations of lines. I already have a b, right? I don't want to use the same letter twice. I took a math class once where the little f on the left-hand side of the equation was not the same as the little f on the right-hand side of the equation, and it was absolute hell trying to understand what was going on. You want to use different letters. I don't want to use something like, Math313 b or something like that. Let's use a different letter. Let's use t. I like s for slope, but that's always dangerous of being interpreted as a 5, so I can understand why the author is choosing to do a t. So when we go through the calculations, we can get a formula for the coordinates. So we get x2 is going to be m squared minus x0 minus x1, and the y coordinate is going to be mx2 plus t. And so this point is the point x0, y0. This is the point x1, y1. And so we get equations for the points. So this is just algebra. Okay. So now that we have this algebra, the next thing is even more algebra. This is one of the reasons why I want to start today's lecture with the Diffie-Hellman equation and the key exchange. That's fun stuff. But at some point, you have to pay the price, and you just have to roll up your sleeves, and you just have to do the work. So recall the discriminant is basically 4a cubed plus 27b squared. I don't really care about the minus sign. And so we have a beautiful, beautiful result. It says that the discriminant, call this a lemma, and you'll see in a moment why I'm not memorizing this, is equal to 27b minus 18ax wait a minute. I'm actually a little worried about this right now. F of x. All right, well, okay, yeah, that's fine. Okay, 6ax squared minus 9bx plus 4a squared f prime of x, where f of x is x cubed plus ax plus b, and f prime of x is 3x squared plus a. Okay. So I was a little concerned when I first started writing this. Why was I concerned for a moment? What can you tell me about the left-hand side? So the left-hand side is just a number. The right-hand side has x dependence. Should I be worried? What must happen on the right-hand side? I'm sorry? All the x's have to cancel. So let's just check the highest power. So I have an x cubed, I have an x to the fourth. So the highest power of x to the fourth is I'll have 18a x to the fourth with a minus sign, coming just from this part. On this part over here, I have an x squared hitting an f prime, so I'll have an 18a x to the fourth. So at least the x to the fourth powers cancel, and almost surely everything else will cancel. How would you prove this? What's the proof? Algebra. Do you have any idea why the hell this is true? Looking at this, do you have any sense? So I'm really trying to drive home a point that I've been trying to make for the last week. That it's very easy to get lost and not really understand what's going on and just, compute. And try to go back and think, what is going on? Why is this true? Why would someone look at these combinations? Well, what's really going on is we're saying that some combination of f and its derivative is going to give the discriminant. There's some deep theorem going on here right now in terms of some kind of linear combination, in terms of writing functions in terms of them. And the fact that this ends up being constant. So there's a lot of interesting stuff going on here. And again, one of the dangers in textbooks and in classes is we present you the material fully formed. I think it's nice sometimes to just see the results, to see that you have a way of verifying that they're true, and then leave it to you as a nice exercise, if you want to. I know how busy this time of year is. There is a reason why I'm trying to cut back on how much I'm requiring you guys to do. But if you want to, if you really think about grad school, try to think about some of these things. Think about where these relationships are coming from. Think about, how would I find a point of order 3? How would I find a point of order 5? Will there always be a point of order 3, 4, 5, 6, 7? If yes, will they always have one of them with rational coordinates? What will the structure look like? This is your chance to investigate. I'm giving you some hints. I'm giving you, here are some clues as to what's out there. This is almost more like Kepler trying to figure out the laws of planetary motion. Newton trying to figure out the laws of planetary motion from Kepler's observations. Kepler observed a bunch of things, and he said to the world, hey, here's a couple of laws. He also had some laws that we have, for the most part, put into the dustbin of history, where he talked about there are 5 platonic solids, and so there should be a platonic solid between the orbits of the different planets. This one is gone. Not just because we've discovered other planets, but there is really no connection between the number of planets we have and the number of platonic solids. It's a coincidence that they both begin with a PLA. Think of yourself like Newton. You've got some clues, you've got some hints. These are empirical observations. Find the theory. You don't have to do it now. You can do it. I know some people are worried that this is their last Monday of a number theory class. You can keep this in reserve for all those Mondays for the rest of your life. It's just something to play with. And try to see, where is this coming from? Okay, so this is where we're beginning to run out of board space. I'm going to erase this stuff over here because I want to keep this discriminant equation alive. And I do want to leave time for the SES today. Okay, so we have this fun fact. All right, the next fun fact is lemma 9.24. So everything is the same as above. E as above, P will be the point x naught, y naught. If P and 2p have integer coordinates, then y naught equals 0, or y naught divides the discriminant. How would you prove this? What are your thoughts? Do the algebra, right? When in doubt, do algebra. Is this enlightening? Maybe. Maybe when you start doing the algebra, you'll get a sense of what's going on. In problem solving today, we did the domino stacking problem. And if you require each domino to be to the left of the previous, it turns out that the way you stack them is the harmonic series. And it took a little bit of a while to see what was going on. And what was fascinating is we actually went back and forth as to what should the length of the domino be. Should it be 1 unit or should it be 2 units? Should the center of the coordinate system be at the midpoint of the bottom domino or at one of the extremes? And depending on how you set things up, the algebra can be a lot nicer or a lot harder. I've talked to you about Morley's theorem, where if you take, well, this is too good of a triangle. If you take any triangle and trisect the angles, the 3 points always form an equilateral triangle. And I may be the only person to actually go through the details and explicitly do the algebra and calculate that the squares of the 3 lengths are equal. And I found that the best coordinates to use was tangents of 1/3 of the angles. Without loss of generality, you can orient things so that this is at 0, 0, this is at 1, 0, and then this is at some intermediate point. You can always put your triangle in a position like this. And you can do games to try to simplify the algebra. And even though it's not that many equations, it still takes a long time to go through this. So here's a claim. We can go through and we can just check and we can do all the different algebra. So the question is, why might we care about a result like this? So they talk about in the book why we care about this. Why would this be useful? So we're trying to understand the points on an elliptic curve. Typically, the more restrictions you put on the coordinates, the harder it is to do the analysis. The easiest is if you allow the points to have any real coordinates, or even better, any complex coordinates. Then you don't have to worry about anything. If you require the coordinates to be rational, that's a little bit of a restriction. I have to make sure I stay within the rationals. Well, it turns out on elliptic curves, it's not so bad. But now if you require that things stay integer, that's much harder. So what if you want a sequence of points such that they have integer coordinates? So here, I want p and 2p to both have integer coordinates. And then this tells us that either y naught equals 0, well, if y naught equals 0, there's only 3 possibilities. Here, here, or here. And these are all torsion points, all points of order 2. They add into themselves as 0. That's what the y equals 0 is essentially telling us. This is the elliptic curve where I have 3 real roots. I could have an elliptic curve with 1 real root. What would it mean? What kind of consequence can you draw from the fact that y has to divide the discriminant? What does that tell you about possibilities? What's infinite? So, good question. How many p have p and 2p having integer coordinates? So I can make this. There we go. So how many times can I get both p and 2p to have integer coordinates? So you're saying that there could be infinitely many? y. What do we know about the discriminant d? Well, we're always assuming about something about a discriminant of an elliptic curve. What are we assuming about it? It will be an integer, but it's not just that it's an integer. There's an assumption we're making about d. And we're saying if d is this, we don't want to consider that as an elliptic curve. I'm sorry? Right, we don't want the discriminant to be 0. The discriminant has to be non-zero. If the discriminant is 0, there is a degeneracy. So we will always assume for elliptic curves that this discriminant is not 0. All right, if the discriminant is not 0, well, either y not equals 0, well, there's at most 3 here. At most 3x work, right? Because if y not equals 0, that means we're on the x-axis. That means x cubed plus ax plus b has to be 0. There's at most 3 roots because it's a cubic. If the discriminant was 0, how many y naught could divide the discriminant? Infinitely many. Because the discriminant is not 0, how many y's could divide? Yeah, at most the number of divisors of d. If you wanted to be really crude, you could say at most maybe twice, because I could have maybe y be negative. Well, but all the negative ones are just the mirror images of the other ones, so let's assume y is positive. So we would have at most, d candidates. Or even better, at most the number of divisors of d. And then you can ask, how does the number of divisors grow? So at most tau of d candidates. Or sometimes people do d of d. There's different notations you can use for the divisor function. So these functions we studied in elementary number theory earlier, they now come into play. They're giving us upper bounds on how many points like this there can be. Now what could happen is we could have a point with integer coordinates, and when we add it to itself, maybe it has rational coordinates. We know that the set of points with rational coordinates is a group. And so you're closed, you stay in that group. So if we add integer coordinates to integer coordinates, it might end up being rational coordinates. We don't know, unfortunately, that integer is closed. That's much harder and almost surely false. That when you look at what's going on, there's divisions that need to go on. It's quite unlikely when you look at all the algebra that integer plus integer stays integer. So this is getting close to an interesting question. How many points are there with integer coordinates on an elliptic curve? Are there infinitely many, or are there only finitely many? This is telling us very easily that if you want both p and 2p to have integer coordinates, there are only finitely many. Well, what if I'm willing to sacrifice, I don't care about 2p, I just care about p. We don't know enough yet at this point to answer that. It turns out there are only finitely many. But this is not quite powerful enough yet to study and answer that question. And so now when we go back to the congruent number problem, this is setting ourselves up for a lot of the analysis, of getting an idea of what the points are like. So again, I don't want to go through all the brute force algebra. I might talk about maybe a higher level approach to look at this problem next time. You can read algebra at home. This is not a good productive use of class time. What I want to do is I want to give you the big picture. What questions do we ask? How do we try to attack them? And a lot of times the first approach is to do brute force analysis. And then later it's to step back. To prove associativity, you can just grind through the calculation. But if you take algebraic geometry and complex analysis, there's this beautiful thing called the Riemann-Roch theorem and the theory of divisors that basically give you associativity for free. It's a much better way of looking at things. And that's one of the themes I want you to get out of this course. That just because you can do the algebra doesn't mean you should do the algebra. It gives you the answer, but it doesn't give you the intuition, it doesn't give you an idea of what's going on. Okay, so this is a good place to stop today so that people will have plenty of time.